So this talk is a little bit different than many of the others you've seen today. This is an academic-oriented talk, but I'm going to try to limit the math and the experimentation to a bare minimum. So right now, many technologists and economic prognosticators are making the argument that we are entering what's called the fourth industrial revolution, or kind of the buzzword version is Industry 4.0. The third industrial revolution started in the 1970s and was primarily created by the introduction of computing and automation into mass manufacturing. The fourth industrial revolution is an extension of that, essentially sensing enabled by IoT devices and machine learning, which can essentially make sense of the sensory data that's coming out of all these sensors, right? And so what I'm going to talk about today is both the benefits and the things we need to worry about when we open up sensing and listening devices in industrial manufacturing and fabrication. So the main reason that industry would want to introduce these technologies into manufacturing is to optimize throughput and efficiency, right? So you can optimize for product quality, you can optimize cost, you can try to reduce variability so that each widget that your factory produces is as similar as possible to its predecessors. And another thing that you can do is you can use these sensing technologies to assess the reliability of your manufacturing equipment as it degrades, right? And, my car's old. I have a little light that tells me when, my airbag needs to be reset or when I need to take it into it to get an oil change, right? But we're talking about large-scale investments here in equipment that is the backbone of many companies' entire being, right? So a lot of what reliability is about is essentially predicting failures of equipment before it actually occurs. So here are two fairly typical Industry 4.0 stories, both of which involve mass production of beer, and both by Anheuser-Busch InBev Corporation. So at the Fort Collins, Colorado brewery, they started monitoring the equipment that they use in their brewery. And they monitored it by listening to the sounds that the equipment made. And it turns out that the most relevant sounds were not anywhere in the human audio spectrum, but beyond our capabilities of hearing. With analytics, they were able to listen, and they would hear changes as the equipment started to degrade, and they'd notice things a few days in advance, and they were able to accurately predict failure hours in advance of manufacturing equipment failing. And at that point, it's much, much better to predict a failure and then go in and service the equipment than to let it fail while you're in the process of brewing beer. Working with Google in Newark, New Jersey, they did not focus so much on reliability. They simply tried to optimize the output. So they were able to increase the length of each filter run by 40 to 50%. The amount of barrelage per filter run they were able to produce went up to 60%, and they were able to optimize the taste of the various beer that they were making there, right? So this is better, faster, cheaper, right? They are able to essentially extract more sellable beer from the same amount of input ingredients going in. They're able to do it faster, and according to their own internal studies, the consumer was perfectly happy with these modifications. Right? So this is the type of thing that you are seeing everywhere throughout industry where people are manufacturing things. Okay? It could be companies, it could be a small-scale manufacturing, everywhere. Now, the main theme of this talk is not to promote Industry 4.0, actually. It's about cautioning you, right? My view is that all of this sensing in data analysis is a security threat. Okay? You might be able to assess the behavior of the physical manufacturing equipment, but an attacker could just as easily use the same exact audio recordings to reverse engineer some or all of what the equipment is doing. Now, the solutions here are not really technical, right? First, secure access to physical equipment, okay? Don't let anyone near the sensors who is not someone that your organization trusts. And the second part is do not, protect the data, right? If you have trusted sensors, don't let the acoustic signals or the electromagnetic signals or any other signals that you are picking up, don't let anybody else access that, because even if they don't have the sensor, if they have the data, they can then reverse engineer your company's secrets. Right? So you need to do both things. Now, the attacks themselves can be very, very sophisticated. The countermeasures are not even technical. Right? So in the rest of the talk, I'm going to shift to a very detailed example. It's a little bit less Industry 4.0. It's really an Industry 3.0 technology that we're just going to stick some sensors around. Okay? And I have some sound recordings. So I'm going to play them, and I'm going to let members of the audience take guesses. Now, we've got a few rules here. If you read the abstract of the talk, and you remember what this is, or if you talked to me over the last few days, you don't get to play. You know the answer. So that's some machine doing its thing. Anyone want to guess what it is? What was that? Sorry, I can't hear you. Failing hard drive. Good guess. Anybody else? No. All right. So here's the big reveal. It's every biologist's favorite toy. It's an Applied Biosciences 3400 DNA synthesizer. This is a machine that makes life. Right? And what may be incredibly surprising is that based on those noises alone, okay, I can recover with 100% accuracy exactly what DNA that machine is manufacturing. Okay? It requires sensing, analytics, and a little bit of domain knowledge from some of my friends in bioengineering. But through those noises, which just sound like somebody cracking a whip, for example, I can actually recover the differences between which bases in DNA, the fabric of life, are being synthesized. So, who cares? Right? I would argue that a lot of people do. There is a huge and growing market for synthetic DNA. Right? We're seeing it in areas like drug discovery, medical treatment. Crop optimization is absolutely huge. Yeah. I've got a great story if anyone wants to talk offline about corn and industrial espionage in that sector. And another emerging area is using DNA as a long-term archival storage medium. Slower, denser, and far more stable than the magnetic tape of my childhood. Right? And so I've got an estimate that next year this market will be around $38.7 billion, and it's only going to grow. Okay? The ability to produce DNA has created new markets. Now, what is the intellectual property concern here? What would somebody want to learn by listening to one of these machines? If you know anything about biology, it's very rare that the person just wants to know what DNA you made. I mean, here's some list of characters that represent the bases. That alone isn't what the real value is. It's a mechanism to get to the real value, which is the actual organism that some company is trying to engineer. Perhaps a new breed of corn that is 5% more drought resistant than anything else on the market, and farmers can then reduce their water supply by 5% and still grow the same amount of corn. That's $1 billion industry right there. Right? So this is what people actually want to know, right? But you're not going to be able to necessarily figure out what went into that corn by looking at the corn itself. You need the DNA to get there. So going back to basics, I'm going to give a slight overview of what DNA is and provide a running description of how this machine works. Right? So DNA consists of 4 main chemicals, C, G, A, and T. Okay? And the way these machines build DNA is they make a single string. Okay? So here we have, going from bottom to top, C, T, G, and A. Now, the 4 chemicals themselves don't directly touch. You have to create kind of a backbone or a skeleton with sugars and phosphates. So if you're going to synthesize synthetic DNA, you're going to have to build that skeleton along with injecting the 4 bases into the system. Right? Now, this is what's called an oligonucleotide, right? So the 4 bases are called nucleotides. So oligo means multiple, so it's kind of a one-dimensional string. If you remember what DNA actually looks like, there's the famous double helix structure, and it's actually 2 strings of DNA that touch one another. So A's and T's bind together, and C's and G's bind together, so that's called complementary bases, right? So if I want to make actual DNA, I need to synthesize 2 strands, 1 strand and then its complement strand, and then put them together. Now, when you're synthesizing DNA, you're synthesizing hundreds of thousands of strands all at once. So if I wanted to make actual DNA, I would have to first synthesize, in this case, 1, then the other, then put them together and shake it up, right? Possibly heating it up as well. Right? But that's what it takes to synthesize the actual DNA that's inside us. Right? So you need to do it. So to make real DNA, you need to do it twice. Don't worry, I can't synthesize you. It's really, really hard. Okay? So a typical oligo that one of these machines can synthesize will have 200 to 300 bases. Okay? Naturally occurring DNA in humans is around 3 billion bases. So even if I could work out the chemistry to kind of concatenate 200 to 300 at a time, the time it would take and the cost would be prohibitive. Right? So I can do interesting scientific experiments with this synthetic DNA. I can't clone you, at least for not now. So now I'm going to talk a little bit about the attack model. Right? So what is an attacker going to do? What does the attacker need? What does the attacker want? Right? So in terms of intent, we're going to assume that the attacker wants to know what DNA you're making or what you're going to use it for. Right? The outcome could be anything. It could be IP theft. Okay? Maybe he wants to sell your information to a competing company or start a competing company. He might have some idea of what your company is doing and have an idea to kind of twist it and make bioterrorism out of it. And that person could then, that's a possibility. This person could work for a competing company, could be a government agent, could be a terrorist. Okay? The attacker needs to know what the target system is and what its known vulnerabilities are. Okay? So in this case, the target system is the applied Biosciences AB3400, and the vulnerabilities, which I'm exposing, are the sounds that it's making. Okay? And I'll get a little bit more specific than that. The attack medium is what's called an acoustic side-channel. Okay? The side channel it's called a side channel because the machine itself is making DNA, but it happens to be emitting this other information in the form of sound. Right? That's just a byproduct. It's not the objective of the machine is not to make sound. What capabilities does the attacker have? Well, the attacker needs to have some mathematical sophistication. This is basically a machine learning problem. What resources does the attacker have to have? Okay? The attacker needs to have one of these machines to be able to train his model. How much will it cost? time, money. If the attacker wants to run one of these attacks, the attacker will have to train a model, which will involve the attacker making DNA on his own machine. That takes time. That takes money. So all of these aspects of the model have to come together in order to have a viable model. Okay? The other thing is that it goes without saying that there's going to be some element of social engineering involved in this attack, because the attacker is going to have to somehow find a way to get a microphone next to that machine. So, what are the capabilities and resources that the attacker needs? The attacker needs to have some idea about how the DNA synthesis process works. I'm going to explain that on the next slide. I am not saying that the attacker needs to understand the chemistry, but the attacker needs to understand the steps involved. Right? This is kind of like knowing what the high-level code is, but not knowing what it's going to look like at the assembly level. The attacker has to have access to the synthesizer's user manual, which will explain how to set the machine up and how the machine works. The attacker will need access to one instance of that machine in order to build a model. Okay? This is a data-driven approach. You can't do it without actual data from an actual machine. Lastly, the attacker has to have some way to place a microphone near the synthesizer. Right? It could be done by wireless transmission, which means that the attacker can place the microphone there once, and then once the microphone, as long as he can get the audio signals, that's okay. Somebody will eventually pick up the microphone. Maybe they'll realize they were hacked. Maybe they'll just throw it away. Maybe they'll go around asking somebody, hey, whose microphone is this? And eventually somebody will get a free microphone out of it. Okay. If the attacker wants to remove the microphone, the attacker needs to return to the scene of the crime and physically take the microphone away. So these are the things that any attacker needs to do. Right? Sounds like I've got Mission Impossible 7 in the scripting phase. All right. I'm not going to go over the chemistry, but this is a 4-step process. So this is a loop for creating DNA one base at a time. Right? There are 4 steps in the loop. Each one of them creates a relevant chemical change in the DNA that you're making. Between step 1 and 2 is when you deliver the new base. That is the part of this cycle that I'm going to attack. The 3rd step, capping, is worth mentioning. You do not have physical control over each piece of DNA, so I cannot take the strand that I'm making and physically take the base that I added and put them together. I've got a lot of strands. I've got a lot of bases. They're sitting together in liquid. I'm shaking them up, hoping that they come together and react and bond, but I can't guarantee it. So what capping does is every time that, for whatever reason, I have a strand that does not actually make a bond with the DNA, I can cap it and prevent it from growing more DNA. That reduces errors in the DNA synthesis process. Right? This chemistry has been more or less settled and mature since the early 1980s. It was invented by a professor at the University of Colorado named Carruthers, who went on to found Amgen. Here's the setup and a little snippet of the user manual. Yeah? So to set one of these things up, you need 2 pieces of documentation. You want the user guide, which shows you how to do it, and you want the site preparation and safety guide. If you're going to train a model on one of these things, you need to do it in a way that's safe. Otherwise, the attacker does damage to the attacker or fails. Yeah? And you need to understand how to set one of these things up. So there's a number of pipes and tubes and a number of different chemicals you need to be able to feed into this thing. So the diagram in the middle shows you how exactly what needs to get set up, what the inputs are, what the outputs are, and it's basically how to hook it all together. And then I've got a photo of the back which shows several of the different aspects that make noise. There are solenoid valves that open and close, so at each stage of that synthesis process, I'm opening some solenoid valves to deliver some chemical into the system. When I deliver a base, I need to open up the solenoid valve that will give me the base that I actually want and not the others. There's pipes, there's pressure regulators, and other things. So After studying this device, we recognized that there were 4 main sources of acoustic emissions, only one of which was actually relevant to this attack we were creating. So solenoid valves opening and closing are what will tell us which bass is being delivered at each time. Fluid flowing through pipes, yes. I mean, if I can distinguish that I've got fluid flowing through the B pipe, that tells me that I've got a B. There's also fans and pressure regulators which make noise. They just make noise. There's very little information that I can take away from those. The reason that this attack works is that every single valve in this system has some unique position, and the AB3400 itself is a big metal device, and differences in position will have differences in audio reflection, and that creates a unique signature when each valve opens and closes, those little pop sounds. The echoes far beyond the spectrum which you or I could hear are a little bit different. Okay? There's also a slight difference in reverberation time, the amount of time it takes the direct signal and the various echoes to arrive at the microphone. So as a result, the acoustic signal that we collect is unique for each valve. The actual attack is somewhat complicated. It involves a fair amount of audio processing and signal processing techniques. I'm not going to go into details here. The main thing is that a lot of that processing is common both to the training phase on the left and the attack phase on the right. We're going to collect audio in each case. We're going to have to pre-process it. We're going to have to extract features. We're going to have to segment the signal so that we identify the time at which basses are being delivered. And then we will have to do more feature extraction on that. And that will allow us to train our model. And then once we have the trained model, those extracted features will allow us to perform inference and make our predictions about which basses are being synthesized. Here's what the attack model would look like, and I do apologize for mathematical formulas on this slide and the next 2, if we're using physics. S is the state of the system, the valves being open and closed over time that are delivering the current bass, and A is the acoustic side channel. Right? So physics happens, and somehow there is a function that could be derived that translates system state to the sound that I pick up. Right? I have no way to derive that, it's too complicated. Right? But it would be ideal. So if I have that function, I would simply compute its inverse, take the acoustic signal, and that will tell me what the system state is. This is all ideal. It's what I'd do if I could. I don't have that power. So what we've done instead is we've taken a data-driven approach, a machine learning, which is that we're creating an approximate function that we are training based on data that we collect. So each bass that we're going to synthesize is an S, and we're going to synthesize a lot of basses. For each time we synthesize a new bass, we're going to get our acoustic emission, and we're going to train a classifier function that will take our acoustic emission and predict the bass that we got. And we're going to use various supervised learning techniques to do that. I'm not going to go into the details. Turns out it's a little bit more complicated than that. As I showed a few slides ago, we need to do some pre-processing on the audio signal to eliminate background noise. We have to isolate the acoustics for each valve. We have to segment the signal. Basically what that means is that I don't care about the noises that are happening when I'm not delivering a new bass. Okay? And then based on the signal segmentation, we can extract features so that I have far fewer features than I have in my raw audio. That's actually really important to be able to train an accurate model. From there, we train the model, and then at the very last step, we apply some domain knowledge which can correct misprediction errors. Here's what the setup looks like. That's a picture of the synthesizer. The microphone is shown on the bottom. We move the microphone basically from either on top of the synthesizer or up to 0.7 meters away from the synthesizer. The microphone that we used is commercial. It's a Zoom H6 audio recorder. We selected it because it's similar to the microphone in an iPhone 4. So this is representative of an attack that somebody could do with a relatively old, out-of-date cell phone. We recorded signals through 3 simultaneous channels, and we also used a contact microphone, which eliminated environmental noise. I'm not going to go into any details about the acoustic engineering here. That's far beyond my comprehension. So we ran an initial training and evaluation step. So we synthesized 7 synthetic oligos. Each one had 60 bases with 15 randomly generated A, Cs, Gs, and Ts, varying orders. So this is purely synthetic. There is no biological function whatsoever. Each one of those runs took just less than 7 hours and 30 minutes. So we had to do that 7 times. We knew exactly which sequences we were generating. So we were able to take the audio signal, okay, and we were able to segment it into different stages and only focus on the stage we care about. So for each run, there's a 787-second initialization stage. That repetitive cycle that I showed lasts 463 seconds, 5 of which are delivering the next base. Everything else is all the other chemistry and cleaning necessary to have this process happen. So a raw audio signal looks something like this. Looks like a bunch of gibberish. And then within there, based on timing, because we read the manual and we understand how this machine works, we were able to isolate the times at which different bases were delivered. So here's a segment of one of those runs, and I've got an A, a C, and a G. And if you look at that time series, there's nothing immediately there which will tell you what's happening. These are not major differences, right? This is why we needed to build a complicated mathematical model. So the raw audio had more than 57,000 individual features. That was way too much to train an accurate model. So our initial feature selection, we kind of just ranked the features by significance, and we arbitrarily chose 75 most relevant features. That led to an improvement, but it wasn't great. Our improved feature selection involved a lot of audio and signal processing techniques, so things like Fourier transforms, wavelet transforms, and things like that. And we ended up with 310 most relevant features, which had the lowest dependency scores. So those were the features that gave us the best overall classification accuracy. So here's what we got. With our improved feature selection, we were able to get 88.07% classification accuracy. So we weren't perfect, but we were pretty good. That we tried, I think, let's see, it's about 4 different machine learning models plus a voting ensemble. And with the improved feature selection, the voting ensemble gave us the best result. So everything I'm going to talk about from now on is going to use the voting ensemble. Of all those bases that we synthesized, we needed about 200 for training a classifier. We experimented with different numbers, and 200 seemed pretty good. And so 80% of the data set was used for training, and 20% was used for validation, and we used tenfold cross-validation. In other words, we separated training and validation data appropriately. In addition to this, we tried a number of experimental trade-offs. I have the raw data as appended at the very end of the talk. I'm going to skip it unless somebody wants to ask me about it. So the overall accuracy tends to degrade under a few different conditions. So for example, when we trained our models using less than 70 samples, that's when we started to notice major degradation in accuracy. So I reported results for 200, which is well over the kind of tipping point. The classifier accuracy is susceptible to noise. So we took our audio recordings and we generated various forms of synthetic noise. Background white noise at 56 decibels or higher seemed to cause significant degradation accuracy, and also people talking in the room around 65 decibels or higher also caused our classifiers to become inaccurate. Right? So once again, if you want to do this attack, you also ideally would eliminate as much noise as possible, or perhaps use a more expensive microphone. Lastly, we experimented by moving the microphone, and we got to about 0.7 meters away, and that's when we started to notice the accuracy going bad. So maybe we could do better with a more expensive microphone. So all of those experiments that I just showed were done using synthetic DNA, just random strings. Next, we start to really mimic what we think an attacker would be after. We decided to do some work with biologically relevant DNA sequences, right? So these are DNA sequences that we know are used in industry, and we can explain the biological function of them, right? So the idea is that what a biotech company would do is, after generating one of these DNA sequences, they would implant it in a living organism, and that would create a protein, right? And that is the secret that the attacker is really looking for, right? Each 3 bases translates into a certain amino acid, and this is the biologically relevant information that an expert could use in order to say, hey, that sequence, these amino acids, this protein, okay, now I know what your real secret is and what your company's actually trying to do. So we worked with 4 DNA sequences that were synthesized. The first one is from a substance called contoxin. This is actually a very lethal protein, but it's highly studied in biotech research. It's highly regulated, but it naturally occurs in snails, okay? Specifically types of cone snails. In short, keep yourself alive. Don't go licking a snail, please. Escargot is safe, don't worry. We also generated a DNA sequence that has been historically used to create human insulin. So prior to 1979, insulin, which is life-saving for diabetics, was actually not extracted from humans. It came from pig pancreases. Right? So if I want to give you insulin, back in the day, I had to grow a pig, I had to kill the pig, I had to extract it. Okay? In 1979, an absolutely huge scientific discovery was made. They found a DNA encoding that could create human insulin if you add this DNA to bacteria. This led to the founding of a company called Genentech, which is still around today, and it's one of the largest pharmaceutical companies in the world. So this is a much more robust and much cheaper way to make insulin. We also generated DNA sequences for 2 peptides, which are used to bind to a protein target called streptavidin, which, if you read enough biological literature, that's a very common protein that's used. All right. Now I'm going to bring domain knowledge into the picture. And this is necessary in order to extract actual value. The attacker doesn't care so much about the DNA, he wants to know the purpose of the DNA. That's what's actually valuable. In order to figure out the purpose, we used a very old piece of software called BLAST. You can Google this and download it. It's free. It was funded by the National Institutes of Health back in the 1990s. And it's basically a database of DNA sequences and their functionality. Right? So the idea of BLAST is that you put in a DNA sequence and it will find closely matching DNA sequences. It doesn't have to be an exact match. You can have a few characters off, and it'll tell you what the likely functionalities are. So our assumption is that the attacker will be satisfied if BLAST gives him a positive match. So here are the 4 DNA sequences. So for each one, on top is the accurate sequence, and on the bottom is what we synthesized. And you'll see that for each one of these sequences, we had a few character misses. So our classification accuracy ranged from about 86.6 to 90.5%. So not 100% perfect, but good enough. In each case, we got the positive BLAST match that we wanted. And that way we could confirm that and we were able to use that to figure out, yeah, this is the DNA sequence we should have gotten. Right? So that's the actual value. In terms of open technical issues, there are a number of things that we could have explored, time and cost permitting. We could have played around with different microphones, more expensive microphones, studio quality microphones, lots of options there, and varied the cost, their capabilities, and the distance. Okay. We only had one of these DNA synthesizers available to us. These things cost about $85,000. You can, for about $5,000 to $10,000, you might be able to find some used, but we only had one. So we used the same synthesizer to train our models, and then we attacked the same synthesizer. Right? A more realistic version of this, the attacker would have his own personal DNA synthesizer, also an AB3400. He would train the model on that one, and then he'd attack a different physical DNA synthesizer sitting in some company's lab. We only had one, and we trained and attacked it more or less in the same 3-month period. So wherever that synthesizer was in its lifetime, the analysis was there. I can easily imagine physical equipment degrading. So it's quite possible that a brand new AB3400 will not yield nearly as much information in its acoustic emissions. And it's possible that one at the end of its lifetime is going to generate so much noise, there's not much useful information that we could glean. So I simply did not have access to enough of these machines at different points in their lifetime to analyze what will happen. I mean, maybe we just hit the sweet spot, and any other time in its lifetime, this attack would not work. I cannot guarantee anything else. The AB3400 is it's kind of the workhorse. It is not the highest end machine. It's a very common machine. Okay? It's the Honda Accord or Toyota Camry of DNA synthesis machines. There are, Ferrari and Lamborghini equivalents out there too. I didn't have access to one that I could hack. It'd be fun to do it again. We also did not investigate possible countermeasures, right? So one of my colleagues let us do this on his DNA synthesis machine that he uses to do his own research and publish Nature papers. As much as I wanted to go into the machine and try to, put my own acoustic padding in there, I respected his desire not to have me break it and ruin his research agenda. Yep. And lastly, it is certainly possible to do similar acoustic attacks on other biological laboratory instruments. We did DNA because we think it's a great story. There's all sorts of machines in wet labs that make noise, some of which you might be able to reverse engineer relevant information from. In fact, one of my collaborators did a very similar attack on a 3D printer. Listening to acoustic noises, he was able to reverse engineer the G-code instructions of the object that it was making. So it was not completely unprecedented when we did this. The difference was that the 3D printer had motors which made a lot more noise continuously over time compared to the individual clicks and pops of the solenoid valves external to this machine. All right. To wrap up, okay, Industry 4.0 integrates IoT sensing and machine learning into all scales of manufacturing with the goal of improving reliability and efficiency. Right? When people talk about Industry 4.0, they're typically thinking of very, very heavy industrial manufacturing, cars, turbines, things like that. Don't forget biotech, nanotech, other emerging things that are much smaller. What I've shown is that sensing, while creating all these other opportunities, also creates side-channel attack vectors. Right? But to get there, you have to use social engineering to acquire those acoustic signals. The other thing is that analyzing these signals in isolation is not enough. You really have to have domain knowledge. You have to know how these machines work, and having some knowledge of what DNA can be used for helped us out immensely. Right? And that's why I'm not the only author of this paper. The best way to protect these attacks is not to come in and do something sophisticated, secure access to the equipment, secure access to the sensory data, encrypt it, put it under good access control. So I need to thank a number of people who contributed to this. So I kind of conceived this with my colleague, Mohammed Al-Farouk at UC Irvine. Will Grover at UCR, he's a bioengineer. He's the one who helped us out with a lot of domain knowledge from biology. John Chaput, also at UC Irvine, he actually owned the machine and let us use it, which was very, very nice of him. He lets his collaborators use the machine as well for their own biological research, and one of them would not allow us to actually listen to her students when they synthesized DNA. She was that paranoid. Because the DNA synthesizer was located at UC Irvine, 3 UC Irvine students carried out the attacks. It didn't make sense to send students from my institution to UC Irvine. Sina, Sujit, and Arnav, of course, are the people who actually did the work. They're the people that matter. Here's some evidence of the conspiracy. So on the left, myself, Mohammed, and Will were sitting around in Will's laboratory talking about contoxins. And there on the right is a picture of Arnav, Mohammed, John, and Sina next to the DNA synthesizer. It's a pretty big machine. And lastly, I need to acknowledge the people who gave me money. So thank you, American taxpayer. I'll take your questions.
Thank you very much for the talk, Philip.
You're welcome.
We have some questions at the document, and I have some other personal questions. So
Okay.
let's start. Would an attack like this be predicated on having the exact same audio setup during the attack as during training?
It would probably help. I don't know if that's an actual requirement. That's another thing that I should actually put in this list. I hypothesize that it would probably work, but I haven't confirmed it experimentally.
Would it even work on a machine that the model wasn't specifically training on?
So if I was to train on one DNA synthesis machine and try it on another, I'm not a machine learning expert. That does sound like transfer learning to me. It could work. At the same time, if it was similar to this machine, yes. Other companies like Twist use a very, very different machine. They don't sell the machines. They just use it internally and sell the DNA. But it's kind of a machine that moves head, that it has a moving head, kind of like a printer cartridge. So it'll dip in the chemical for adding a certain base, and then it will go around pointing and dropping that chemical on the sites where it's going to grow the DNA that's going to have that base. I think that machine is so fundamentally different than these that you could not apply transfer learning. But other machines that are similar, that are a bit older, it possibly could work. But I haven't confirmed it.
Okay. Let's wait a second because someone is writing a question. Okay. How practical is this attack, actually? The result seems fun and exciting, but will we see a real case of this being used in the wild?
So I would say that now that we let the cat out of the bag, no one in their right mind would ever let everyone who's actually paying attention to this is going to make sure that there's no cell phones anywhere near their equipment. So my goal is that no one ever does this, right? Because if we didn't publish it, then somebody could have figured it out. Now, how practical is it? I mean, there are definitely some logistical challenges on the social engineering side. I could rant and ramble about known cases of industrial espionage, and not necessarily cases that involved a cybersecurity attack, but people will do crazy things, right? So what I'll do is I'll give you the name of a person, and you can Google it, and you can read his story. His name is Mo Hailong. First name is Mo, M-O. Last name is Hailong, H-A-I-L-O-G. He used social engineering to discover the location of research cornfields in Iowa, and he actually went to the fields and he was caught scooping up corn, some of which he managed to send to the company in China that employed him, and it turned into a 5-year FBI investigation. 6 people were indicted by the FBI, 5 of which are in China and were out of their reach. Mo Hailong was sentenced to 3 years in 2016. Right. So, and he was essentially trying to get at hybrid corn. Right. So there was no cybersecurity element to what he was doing, but if somebody wanted to get at the genetics, you could try something like this.
Okay. I have some questions related with the time series analysis itself.
Yes.
Because you apply machine learning algorithms against a summarization of the time series. I mean, the summarization, I want to say that you extract features of the time series. How many features do you need, or do you need it to summarize correctly the time series and train the model correctly? So
in terms of the total number of features we used, we ended up with 310. This was kind of our best result. Now, at that point, we had already transformed the time series, so it was in the frequency domain, fast Fourier transforms, wavelet transforms, things like that. So to connect to earlier talks, we tried the matrix profile and it did not work in this case.
Yeah, but you extract that, but then you filter what features are really interested for the summarization, no?
Yes.
And after that filter, what was the result? And could you mention what features or statistical values are the most interesting?
It's rather it's buried in the paper, and we didn't actually give a list because it's kind of, it's different pieces of sound, transformed at, that correspond to different pieces of the signal. So it's nothing that really makes sense to a human. It's not like, okay, well, do a convolution or something. So with the raw signal, we got about 25% accuracy, which is as good as a random guess, right? I mean, there's 4 bases, so if you're 25% accurate, you've got a 1 in 4 chance, right? Using all 50,000 features, we got up to 50% accuracy. Okay? And then when we ranked those features and chose the top 75, that got us to about 65% accuracy. And then the improved feature selection, which I kind of skipped over a little bit, that's with 310 features. That got us to about, 88.07% accuracy. Right. So here, we analyzed the audio spectrum and we looked at the frequencies. So, we recognized that anything above 300 hertz was irrelevant, and it was a fair amount of audio processing and signal processing there.
Okay. And the last question: Could you come back to the slide where there are the
Yes.
Why did you? Well, I suppose that you test or you train those classifiers.
Yes.
And then you choose. Why did you choose those, or why do you think those classifiers are the best for that task?
Time. I mean,
okay.
So I was a little bit harsh on this. I hate when a paper says neural network. That could be anything, right? I mean, in this case, it was a relatively small neural network with these parameters, but I mean, if a neural network is a graph, there's infinitely many topologies, infinitely many sizes, and we certainly did not sweep the entire space of potential neural networks. So I definitely think that, with a bit more, because we're not really machine learning experts, but if we had gone in that direction, we probably could have found some type of neural network, probably a one-dimensional convolutional neural network that could have done better than the individual neural network. It's just one of those things that's kind of infinitely deep. And to be honest, we just wanted to get this thing over with.
Okay. Let me check if someone wrote another question. Yeah. Could placing sounds to infer with the listening espionage help?
So basically, can adding noise help? Yes. Right. So we took the audio signal and we added different types of noises, retrained our classifiers, and looked at the accuracy. Right. So I'm not going to go over the meaning of white, violet, pink, brown, but for example, you can see that around 67 decibels, when you add the noise of people talking in the room, the classifier accuracy degrades. Even lower, you start seeing degradation when you start introducing white noise, violet noise, blue noise, and things like that. So yes, you definitely can make a bunch of noise. Now, the issue is, how big is your lab space? Okay. If you have people who need to work in that space, they might not appreciate all of a sudden their workspace being polluted with noise to prevent this type of attack, right? It could even lead to health concerns, audio issues. So if you don't consider the human element, yes, this is a great countermeasure. When you actually think that people are going to be there, it might not be practical.
Okay, so that's all, Philip. Thank you very much.
Thank you.